Solvation can have a stabilizing effect on a conjugate base. So if we look at water, here's the water molecule. If water donates this proton, then our electrons in magenta are left behind on the oxygen, which gives the oxygen a -1 formal charge, and we form the conjugate base to water, which is the hydroxide anion. The hydroxide anion can be stabilized by our solvent. So if water is our solvent, let me go ahead and draw in a few water molecules here. So here is one water molecule. Let me draw another one over here. We know that water is a polar solvent. It's a polar molecule. The oxygen has a partial negative charge and the hydrogens have partial positive charges. That's because the oxygen is more electronegative than hydrogen. And now we have a situation where opposite charges attract. The partially positive hydrogen on water is attracted to the negatively charged oxygen on hydroxide. So there is an attractive force between these opposite charges. And that attractive force stabilizes or helps to stabilize the negative charge on the hydroxide anion. So over here we have another water molecule, so partial negative, partial positive. We have another stabilizing force, another force to help stabilize that negative charge on the hydroxide anion. So the more water molecules you have, the more solvent molecules you have solvating your anion, the more stable the conjugate base. So if we look at our four compounds over here, so water, this proton on water has a pKa value of approximately 15.7. For ethanol, this proton has a pKa value of about 16. For isopropanol, this proton has a pKa value of 17. And for tert-butanol, this proton has a pKa value of about 18. The lower the pKa value, the stronger the acid. So water is the strongest acid out of these four because water has the lowest value for the pKa. If water is the strongest acid, that means the conjugate base must be the most stable. So the hydroxide anion is the most stable out of our conjugate bases, and that's because we can fit more water molecules around our hydroxide anion. The hydroxide anion is the best at being stabilized, the best at being solvated by our solvent. And that's because of something called steric hindrance. So attached to this negatively charged oxygen, we have a really small little hydrogen. When we look at the other conjugate bases, so this is the ethoxide anion, which is the conjugate base to ethanol. We have a CH2 here, and then we have a CH3. CH2 and CH3 take up more space in this hydrogen. Right, as we go down, we see even more stuff, even more steric hindrance. This carbon right here is attached to a hydrogen. It's also attached to a CH3 and a CH3. So we have even more stuff to get in the way. And finally, for our last conjugate base, this is called the tert-butoxide anion. We have a carbon attached to a CH3, a CH3, and a CH3. So even more stuff to get in the way. And that steric hindrance, those bulky groups, prevent the interaction of solvent molecules with our conjugate base. So if I draw in a water molecule here, so there will be some stabilization, right? We know oxygen is partially negative. We know that hydrogens are partially positive. So there is an attractive force between our opposite charges, and that would help to stabilize the conjugate base. The problem is these bulky CH3 groups prevent a lot of water molecules from being able to stabilize this conjugate base. And that means that this tert-butoxide anion is the least stable conjugate base. As we move up in this direction, right, we're decreasing in steric hindrance. We go from 3 bulky methyl groups to 2 bulky methyl groups to 1 right here, and then finally to this hydrogen. So we're decreasing in the steric hindrance. We're increasing in the ability of our solvent to solvate our anion and stabilize our anion. And therefore, the hydroxide anion is the most stable in our solvent. If this anion is the most stable, that means that water is the most likely to donate its proton. And that's why we see the lowest value for the pKa.